Example 5.9 is a really good problem because it ties in the limiting reactant ideas from chapter 4 with the thermochemical ideas from chapter 5. And if we look at this example, which involves the death of a gummy bear reaction, we have sucrose, right? That's a relevant bit of information from the problem. 2.67 grams of sucrose, right? C12H22O11, and 7.19 grams of potassium chlorate. So 7.19 grams of KClO3. And if I'm to relate these two in a balanced chemical equation, I'm just going to try and make this a little clearer. If I'm going to try and relate these two in a balanced chemical equation, yeah, I guess that's not any better. Then what I need to do is first convert them to moles, right? That's a key idea from stoichiometry. So my first step would be to find the molar mass of each of these, right? So for sucrose, I take 12 carbons, 22 hydrogens, 11 oxygens, add those up together, and you should get 342.3 grams in 1 mole of sucrose. Do the same thing for potassium chlorate, right? 1 potassium, 1 chlorine, 3 oxygens, and you should get 122.6 grams in 1 mole. Okay. So I convert both of those values over. Okay. My 2.67 divided by 342.3 and my 7.19 divided by 122.6 tells me that I have 0.00780 moles of my sucrose, and I have 0.0586 moles of my potassium chlorate. But I can't relate those two directly together because that's not a one-to-one molar ratio, right? They're not stoichiometric equivalents. If I look at my balanced chemical equation, it's 1 sucrose in the aqueous phase plus 8 potassium chlorates in the aqueous phase go to 12 CO2s in the gaseous phase, 11 H2Os in the liquid phase, and 8 potassium chlorides, again in the aqueous phase. So if you recall from chapter 4, to calculate the limiting reactant, what I need to do is pick a product and figure out for each of these how much of that same product can they make. You can choose any one of these three. You'll find the limiting reactant the same way regardless. I'm going to choose potassium chloride. Okay. So my 0.0078 moles of sucrose, when I use my stoichiometric equivalence, it's 1 as my coefficient from sucrose to 8, my stoichiometric equivalent for potassium chloride. Right, so I take my 0.00780 times 8. Tells me that that could make up to 0.0624 moles of KCl. I do the same thing for potassium chlorate. I had 0.0586 moles of potassium chlorate to start. And that's why I chose potassium chloride here, because those stoichiometric equivalents are the same, 8 to 8, which makes this math a little bit easier. Those 8s cancel each other out, and this could make 0.0586 moles of KCl. Whichever number is lower here, right, that can make less. So if I go backwards then to what I started with, right, my conclusion here is that potassium chlorate is LR, the limiting reactant. And that's all old information from chapter 4. Okay. So now the question is, right, it tells me 43.7 kilojoules is released which means that if it's being released, the reaction is exothermic, right? Delta H is equal to negative 43.7 kilojoules, right? Negative because it's exothermic. But it was 43.7 kilojoules for the reaction as we were given, right? So negative 43.7 kilojoules is released for that amount of potassium chlorate, 0.0586 moles of KClO3. And I want to know what the heat of this reaction is up here exactly as it's written. So the simplest thing to do is just set up a proportion, right? If it's negative 43.7 kilojoules for 0.0586 moles of KClO3, right? How many kilojoules does that work out to be for 8 moles of KClO3? Because that's what I'm solving for, the heat of this exact reaction when I have 1 mole of sucrose and 8 moles of potassium chlorate coming together. So that goes down here.